going? Okay. Let's have a look. So, yes, I appreciate after lunch you guys as a group tend to be very chatty, but you've got to get on top of that. Okay. To understand that exothermic reactions release energy, to understand that endothermic reactions require an input of energy. Those are effectively, that's year 9 right there in one slide.
Oh, that would be nice.
You should have done. Okay, can I change?
Yes.
Okay. Now, that there is a pretty good cram card right there. So let's work through this slowly. Okay, you need to understand these particular ideas. Exothermic reactions, the reactant bonds are high energy and the product bonds are low energy. Where have you seen this before? You should be writing this down, yes. Where have you seen this before? Hydrocarbons in combustion reactions. When you burn a hydrocarbon, the hydrocarbon has high energy bonds. The waste products have low energy bonds. Examples, and this is an example of an endothermic reaction. You'll need to understand how energy level diagrams work. You'll need to understand activation energy, and you'll need to understand this idea, enthalpy or negative. Enthalpy is negative in an exothermic reaction, so we'll be covering all of that. The opposite case is true for endothermic reactions. The reactant bonds are low energy and the products are high energy. And I gave you an example of an endothermic reaction, or a type of reaction where that sort of thing happens in photosynthesis, where the low energy, the bonds, the reactant bonds are low energy in the form of carbon dioxide and water, and you end up with glucose, which has high energy in its bonds. And again, we're going to look at activation energy, this idea of activation energy. We're going to look at energy level diagrams and how to read those. And we're going to talk about enthalpy, which in this case is positive. Okay? And you should almost be able to work out what's happening with enthalpy just based upon that initial bit of information. Now, can I change? Well, as I said, most of these, this is the main point here, but you won't understand what these 3 points are down the bottom. And so we'll just work through those one at a time. Yes?
Is enthalpy like the way the energy...
Yeah. So, in fact, enthalpy here is positive because energy in the bonds has increased. Whereas in enthalpy down here has decreased, meaning that the product bonds have lower energy.
Yep.
Okay. So, let's have a look. Okay. Again, exothermic reactions, and you can see here energy being output in this particular case, whereas in an endothermic reaction, energy from the outside environment, maybe as sunlight, is pulled in here, and you end up with, in fact, this is sunlight. There is no ifs or buts. That's photosynthesis. So that's your best example of a naturally occurring endothermic reaction. Exothermic releases energy as light or heat. So if you burn a fossil fuel, you release carbon dioxide, water and energy. And that heat is really a reflection of the bonds in the fossil fuel being broken and in combination with the oxygen and producing low energy carbon dioxide and water, and that difference in energy is that heat that you feel on your hands.
Yep.
Now in photosynthesis, here we have low energy carbon dioxide and water, and with the input of energy, and you need, of course, what's the molecule in photosynthesis that's responsible for sunlight being captured and glucose? No, the molecule chlorophyll in place. Yep. They're good examples of that. You don't need to write down these particular equations, but you do need to see that this energy is a product here, whereas energy works. It's not quite a reactant, but it works in that way. Energy must be input in this system in order for the reaction to occur. Photosynthesis is the best example of this. And at year 10, at year 9, year 10, and certainly if you do a biology, you would be expected to know the equation for photosynthesis. Now, if you want to write that down perfectly at a year 11 level, you'd actually put chloroplast. You could put chloroplast. Actually, I'm going to put chlorophyll. That's even better. Chlorophyll in the chloroplast is responsible for capturing that energy as sunlight and producing glucose as this high energy molecule. And of course, cellular respiration takes that and then produces ATP in the mitochondria. And then you've got oxygen as a waste product, which is great for us. Okay, can I change?
Yeah.
I'll give you a generous 30 seconds. It's online as well. Okay. Now, I'll just change quickly and we'll have a look at this. Now, you've seen this before. Stop wasting time. Okay. Exothermic reactions release energy as light or heat. Okay, you know that energy is held in chemical bonds. And I showed you this diagram once before. Do you remember? Yes. We talked about hydrocarbons. And I said that the energy here is in the bonds. The reactant energy over here is high energy. The energy in the bonds over here of the products is lower. And that difference is the energy that's released. Okay? So, energy is released as heat or light to the surroundings because the bonds formed in the products have lower energy. And you need to understand that idea. And that idea in red is what you need to certainly write down. The reactant bonds have high energy, the product bonds have low energy. So the reactant bonds have higher energy than the product bonds. And the example, of course, is a hydrocarbon or anything that combusts. That will always be the case. You don't burn something and get a product at the other end that has more energy in its bonds than you started with. Okay.
Can you write down the in molecules bit?
Which in molecules bit?
The second one.
You should already have that from the hydrocarbons, because that slide was in hydrocarbons. But you certainly need to understand this idea that energy is stored in chemical bonds. You're not breaking atoms, you're not making atoms. You know, you don't get energy out that way, you just make and break bonds. Yes?
Why can't it all just be the same? Like the bonds?
I'm
Why can't a normal bond amount go to a normal bond amount? And
It's, well, you know from your periodic table that different atoms and different elements have different electron affinity.
so is that why heat and light is produced?
Well, that's why bond strengths vary between molecules. Even though carbon, you know, might appear in huge numbers of molecules, but the amount of energy that is stored per gram of that substance will vary depending on effectively how they fit together. Yeah. So the bonds aren't the same, you know, which is, I'm just thinking in terms of what type of universe would it be if bonds all had the same amount of energy. I don't know. Would there be life? I don't know. It's a complicated idea. Well, one of the, like, for example, plants. What plants are doing is they're taking low energy products and they're making a high energy substance.
Well,
I don't know.
Would everything be
So anyway, that is the universe we live in. Now, by the way, if you're talking, I'm assuming you finished.
Oh, yeah.
Okay, so I can change. Now, no surprises. Okay, there's our example of an exothermic reaction, combustion. You can see here, see see here CH4, high energy, oxygen, high energy. The oxygen combine ultimately with the hydrogens to produce H2O, and the carbon combines with the oxygen as well to produce, carbon combines with the oxygen to produce carbon dioxide. So that is a balanced and exothermic reaction, a combustion reaction. Now, you already have all of that information. That's all covered already. Now, example of exothermic reactions. Now, write down some examples. Burning, detonation, which is the same thing, acids with metals, okay? And I'll give you a minute to think about those 5 examples, whether they are exothermic or endothermic. So definitely write down some examples.
What's that? It's actually burning in the corner.
Yeah, what is that like?
Oh, I'm not sure what that is. It's kind of cool, but you can see it's actually,
It's like a volcano going on.
yeah, it's just throwing debris out. The debris takes up more room than the original product.
Yeah.
Does the camera like pick up noise as well? Like,
Yes, of course.
well,
Otherwise it wouldn't work as a system.
Does the camera put a move?
Can the camera video?
Yeah. It neither picks up noise nor video. Okay. Okay. Let's go quickly. Now, if you think exothermic, hold up your right hand. If you think endothermic, hold up your left hand. Okay. Charcoal burning.
Which one was which again?
Right hand is exothermic. It would be exothermic. Candle burning. Exothermic, yes. Now, what about a kettle boiling? Now, how is the kettle boiling? Is it?
It's energy.
I know, but it's releasing energy, but is there fire going into it underneath? So some people, that one, they look at it like a system and they go, oh yeah. But most people would say exothermic because the energy is being released into the environment. What about ice melting?
It's chemical.
No, we're not talking chemical and physical change. We're talking exothermic and endothermic.
None of it.
Okay, so ice melting would be exothermic. A firework. Sorry, did I say exo or endo? Let me have a think about that. No.
It's still
so it increases in temperature.
It's not a matter of temperature, it's a matter of
energy.
yeah. So, but in order for the ice to melt, it has to absorb heat. Yes?
It says a kettle boiling is endothermic.
Where does it say that?
Like down the bottom.
Oh, there we go. Oh, so the answer's there. Oh, that makes it easy, doesn't it?
So a kettle boiling is not exothermic?
Hang on, there you go. Ice melting is endothermic. There you go.
Endothermic.
Yeah.
Endothermic. Did I say exo or endo?
You said extra.
Oh, I'm sorry, I meant
Hold
endo.
on, is a kettle...
A kettle boiling,
Because the water gets hotter.
it depends how you look at the system. If you're looking at energy being put in from the bottom, it's endothermic. Like, so if it's sitting on the gas and you're putting energy in, but if you're just looking at the kettle by itself, you'd say, well, okay, it's probably exothermic because it's emitting heat into the environment. So it depends how you look at it. And a firework exploding, anytime there is burning or combustion, it's exothermic. Okay, anytime you have those two things. Now, let's have a look. Right. Now this is another example of exothermic. We used to do this prep. Now, notice there, magnesium metal going into an acid and look at the temperature change. Magnesium going into hydrochloric acid, and you would have done acid metal reactions last year, and the test tube does get warmer. So that is an example of an exothermic reaction. Okay, now here is endothermic. A process or reaction where the system absorbs energy. You've already seen this before. The key point here is bond energy again. The reactant bonds have lower amounts of energy than the product bonds. This carbohydrate here as glucose has high energy bonds, whereas these reactants, water and carbon dioxide over here, have low energy bonds. And it's the chlorophyll in the chloroplast that is capturing the light energy here and resulting in a high energy product. Okay, endothermic reactions don't occur very often. Most of the reactions you'll think about are going to be exothermic. They're the ones you're familiar with. Yep.
Does that mean that endothermic reactions have to absorb more energy to counteract for there being more exothermic reaction?
No, I don't think it quite works that way. I'm just.
Did you know what tomatoes are tomatoes?
Yeah.
It's confused. To be honest, I'm a little bit confused. But anyway, those are. That's the key difference. I think I have an energy level diagram. No, I do not. No, I still do not. Okay. So, if
Is
you
that what you were looking for, Mr. Maz?
that one there. Hang on.
Energy level.
Now listen up. If that is the energy level diagram for an exothermic reaction, what would it look like for an endothermic reaction? Yeah.
They'd be going that way.
Yeah, you would need to see something along the lines of low energy, high energy. So this is your reactants, this is your products, and reactants are water and carbon dioxide, and products glucose. Okay, that would be the energy level diagram for that particular system, an endothermic reaction. Now, let's have a look at that. I've already mentioned this before. Photosynthesis is the best example of this. That's the equation there. That's the proper equation for Year 11 biology, and I suppose Year 10 biology as well. So if your equation that you wrote down before doesn't quite match that, then you should make that change. A few endothermic chemical reactions, they're pretty rare. So you can get a few reactions that give off gases that are endothermic, they get very cold. Dissolving salts in water is another process that is often endothermic. Has anyone got an example of that last one there, the one with the red dot? Dissolving salts in water to get an endothermic reaction. What do you think cold packs are? So you get like, oh, I've hurt my knee, I'm playing foosball or whatever it might be. And so you come out, they break the pack up, which is releasing the solvents of the water, and you pack that on your leg, and that system, in order to run, needs to absorb energy from the surroundings. And of course, also it becomes cold in its own right, and so you get that cold pack effect. So rather than having to have ice on hand, you can just have this particular reaction ready to go. Okay. Let's see. No.
Does that make extract that heat out?
I really need to look that up, that particular chemical equation, because of course the grill on the back of the freezer and the fridge is quite warm.
Just
So-
really tight. Does it run like cycle the air through the thing at the back? Or you
I think that's for dissipating the heat. So that's why it's got the grill type effect. Okay. Now,
No.
not wasting time.
Foosball.
Can I change?
Yeah.
Okay. Okay. Compounds. This is your example. If you're asked for an example of an endothermic reaction, Colpax. Okay, you won't necessarily need to remember the salt, but you should remember that certain salts, in this case ammonium nitrate, when mixed with water, will produce a product that is colder than the environment around it. So, again, guys, it's still being too noisy, still wasting time, which is problematic for me. Now, lastly, okay,
What?
there we go.
What is that?
There we go.
It's like a Yeti.
Come on. There we go.
Oh, really? I didn't know that.
Right. Okay. Now, right. There's 4 more examples there. Are these exothermic, endothermic?
Yes.
Have a think about this for a little bit. A red glow spreads throughout the mixture and the temperature rises. Yeah, you should be thinking exothermic. Okay, the mixture bubbled vigorously, but the temperature dropped 15 degrees. That would be endothermic. Hydrazine and hydrogen peroxide react explosively. Exothermic. The decaying grass in a compost maker was considerably warmer than the outside temperature. So it's exothermic again. Okay, I think I've got the answers down the bottom. Oh, did. Oh yeah, I did.
Okay.
There you go. Now,
So if they're doing like stuff illegal, say
right,
you're in.
let's have a look at this.
Well, that's off camera, right?
Okay. Energy level diagrams. This is problematic for a lot of students, but we'll have a look at this quickly. Okay. Now, actually, do I need to look at that? Okay. Let's have a look at this. Activation energy, you'll need to write this one down. Activation energy is the energy needed to begin a reaction and break chemical bonds in the reactants. So, some reactions occur pretty easily and others do not. Now, remember when you put energy into a system, heat into a system, you get more atomic motion. Atoms move faster, the vibrational energy increases if you like. So you've got molecules that will hit each other, and if they hit each other hard enough with sufficient force, with sufficient energy, you can end up breaking bonds and making bonds. And here's this idea of activation energy, where you've got your 2 hydrogens over here and some oxygen. Okay, and if you give them enough energy into that system, you'll end up producing water molecules in this case and energy. So a little bit of energy needs to go in, and then you have your water as a product afterwards. Now, is that an exothermic reaction or an endothermic reaction based upon that diagram? Just look at the energy levels. Yeah, exothermic, and why is that?
Lower energy for the product.
Yeah, the products are low energy products. So you have higher energy reactants, lower energy products. That is an exothermic reaction. Yes?
Burning longer chain hydrocarbons, do they have like a higher activation energy? Is that?
Yeah. It takes more to get them started,
Yeah.
but then they'll go. And it's harder also to burn them with complete combustion because they're thicker, they're more viscous. Remember, when you're burning things, you're burning a vapour. You're not burning the solid.
Yeah, you can't burn the road.
No. You know, so you need to vaporise them first.
Yeah.
Now, there we go. Guys, draw those quickly. That is the energy level diagrams for exothermic and endothermic. In exothermic, now, in a reaction there, for an exothermic reaction, you need to input a little energy. So this is your, we'll just say, we'll give that a random number of 10, we'll give that a random number of 2. The products here have lower energy than the original reactants did. It's an exothermic reaction. this is the overall change in energy. That one there, okay? Record each of those. Like that, label those diagrams exactly like that. That will become important in a little bit, okay? An endothermic reaction, you still need to put a little bit of energy into the system. There's your activation energy. You still, actually, it's considerably more. That's your activation energy there, and that gets it going, and then you have higher energy products, and there's your overall change in energy. So copy those two diagrams exactly, because those are the textbook diagrams for exothermic, endothermic, if you like. Have you done that?
Danny.
Oh, you found your Martin King.
Quick. No rulers, just get it done. Because there's one more thing I need to cover. And we only have 4 minutes, 40 seconds.
Oh, yeah. Almost done.
Now we need to talk about this overall change here. That's key. Okay. So, notice here the amount of energy has decreased. So the energy in the bonds here was 10 to begin with. The energy in the products has dropped down to maybe 2. There's been a decrease. Whereas if you notice here, the reactants had low energy to begin with. The products have high energy. That arrow only goes to there, and that is a positive change, and that's enthalpy. Yeah?
Why in the exothermic one, the activation energy sort of shows that difference in where it's at its peak from where the reactants are.
Yep.
And the endothermic is like horizontally across it. How does that work?
I'm not sure. This is just pointing. That's the activation energy there, and that's the activation energy there. Yeah. So it's just pointing. It would have been better to have that on the other side. Would have made it clearer. Okay. I'll change quickly. Okay. That is. Oh, hang on. That's still frozen. Okay. Here is an exothermic reaction, and here's this idea of enthalpy, or heat energy of a system. Enthalpy is negative in this system. And why is that? Because see that difference there? Where did that energy go? It's actually exited the system as heat and light. And so overall, the energy, so on your diagram here, in overall energy change, put enthalpy, and the symbol for enthalpy is that enthalpy is negative, and it means that the energy in the bonds has been reduced in that system. So enthalpy, total heat content of a system, enthalpy is negative in exothermic as heat is lost to the surroundings. You need to write that down. You need to write down the opposite of that for enthalpy in an endothermic reaction. In an endothermic reaction, bond energy increases, so enthalpy is positive. I'll just show you this quickly, is that okay? Triangle means the change. Yeah. There is the There is the energy level diagram for an endothermic reaction. Heat is taken in, so enthalpy is positive in this case.